We're all set. So thanks, Afia. And that's all of us. Listen and enjoy.
Okay, thank you. Hi everyone. My name is Achia Eliasaf. I'm a member of the BGU Ben-Gurion University in Israel, and the topic is automatic code generation. And I'm actually going to present. Okay, it's not moving. Yeah, it is. So I'm going to present three different works that I'm working on or published during the past years. Generally speaking, I think we can divide, maybe there are more ways to divide this topic, but until, I don't know, until the breakthrough of LLMs, there were mostly one way to do code generation, which was one of the prominent ways or the most used way to do a code generation was using genetic programming. So for years, this approach in the middle was one of the known ways. Gen Prog, I think, is a industry tool for improving, or Eversuite, I don't remember. One of them is a industry tool for improving code, for detecting and patching buggy code. And so there are many, there's much work on improving existing code into a better code. And improving can be patching indeed, or maybe improving the runtime, or improving the memory allocation and stuff like that. And the reason that generating a complete code from scratch is not that popular, at least not until this late breakthrough of LLMs. And the reason that it wasn't very popular is that the search space of generating code from scratch is huge. If you don't have anything to rely on to start from, then the search space is huge. But what I'm going to do, I'm going to present two approaches, two works that tries to, why is it's not moving? I know. Okay. Two approaches that use genetic programming to generate a complete system, complete program from scratch. And then I'll conclude with a in-progress work on translating requirements into a working system, which is a bit different than what we are used to with the GitHub Copilot and ChatGPT. So the first work is a joint work with Irena, Gera, and Oded, which are also here. It's accepted to Gecko 2024, so Irena will present it soon. And this work is about a game. It's an assembly coding competition, which is called CodeGuru Extreme. Oded is, I think, one of the founders of this competition. It's a competition that has been taken for place every year since 2005. And the competitors are outstanding high school students, and each year the level rises, and the competition is much more sophisticated than it was at the beginning. And the purpose of this competition is to generate Survivor. Survivor is a short 8086 assembly program that is, and you have this arena on the right side. You can see the arena, and the arena is loaded with, it's a shared memory loaded with survivors. And the goal is to defeat other survivors. And the way you do that is by causing the opponent to run an illegal command by overriding its memory. And so you generate survivors that try to write in several places all over the memory. And the more you write, the faster you write, and the more you write, there are more chances that you will hit someone else, and you will cause it to run illegal command. And the colors here are different survivors. Each survivor has its color, and you can see how it's running and what it does on the memory. So this is the arena and the simulator for the game.
Each dot is a survivor?
Each what? Sorry?
Each dot and the picture is a survivor? How do you...
So yeah, you can see here there are 4 survivors. These are the colors of the survivors. Some of the survivors has only one part of code, and some of the survivors has 2 parts of code. And you see the colors on the right. These are the places that they wrote
I see. Okay.
data on the shared memory. And the programs themselves are short assembly programs. So it's kind of a cyber competition. They really need to get familiar with cyber techniques and assembly and low-level programming. And the approach, the goal of our paper, what we try to do, is to evolve good survivors that will win the top human survivors by finding their weaknesses. So basically play the competition. But as I will show, we are not exactly playing by the rules of the competition. There is a small difference, and I will expand on this later. And we use evolutionary algorithms for this task, which is heuristic, stochastic heuristic search algorithm that is inspired by the theory of biological evolution. And for those who are not familiar with evolutionary algorithms, so what we do, instead of generating a single solution and trying to improve it, like in, I don't know, neural networks, for example, what we do is we create a population of solutions. In this case, each solution is not a turtle, but it's a survivor, CodeGuru Extreme Survivor. But here it's a turtle. So we have a population of solutions to the problem that we try to solve. And then we evaluate each of these individuals, and we select them. The fittest survives. So we select them randomly, but with better probability for good individuals, for highly ranked individuals. And then after we select them, we reproduce them using the crossover operator, which we will see. And we get a new type of individual. And then we add the mutation operator. And finally, we get the new population for the next generation. And so it goes on and on until we are satisfied with the result and we can complete the learning algorithm, and we get an individual at the end that is good at the task.
Shayaw,
Yeah, maybe you can mute him.
can you go on mute?
Okay, sorry.
Okay, so for evolving CodeGuru survivors, we need to define how we're going to represent these individuals, these solutions, these survivors, and how what are the genetic operators that we are going to use for recombining them and mutate them, and of course the fitness function to evaluate them. And so our first task was to represent these programs as individuals that we can play with, we can work with. And we started, Irena started with generating a context-free grammar for assembly. So the grammar is much longer than what you see here. And it's basically all the rules, the grammar rules for creating random programs. And these programs are represented and coded as trees. But of course, we're not watching at the tree representation. We are watching at the final representation, which is just a basic code. And you see that each individual has two parts. These are the rules of the game. And so there are two parts, the left and the right parts of the survivor that was randomly generated at the first iteration. And then for those who are not familiar with genetic programming, we can take two parents and cross over them. We can cut them at a random point and then recombine them again. On the one gets the other side of the other parent, and then we get a new child or new two childs in this case. And we can also mutate them by cutting one of the subtrees, random subtree, and growing a new subtree instead. So this is basic genetic programming. And here comes the part of the fitness function, which is one of the most important parts for evolving these individuals. So how we evaluated the individuals. We have a program, we have a random program, we want to evaluate it for evolving it. And so we ran 200 battles with a winning human written survivor. So we took the past years winning survivors. The competition is open, and the code from previous years is open source. We have an access to all the best and winning survivors from previous years. And so we ran 200 battles against a single winning human written survivor. And then we combine all these ingredients. We have the engine score, which combines how many times it won and how long it survived and so on. So there's the engine score. There is the lifetime, the average number of rounds the survivor stayed alive. The written bytes, the number of bytes it wrote, and the writing rate. How fast it writes bytes into the shared memory. So all these parts, all of these parts of the fitness function are combined together into some formula. I'm not going to show it because it's not very interesting. But at the end, we have a formula that takes into account all these parts and give a fitness function and a grade to the individual. And so we have all the parts of the evolution, and we want to see how it worked. So this is the part of the results. What you see here is the human survivors, the winning human survivors since 2006 till 2 years ago. And what you can see here is the number of times that we won this survivor. So in most of the cases, we won 8 out of 10 wins, 8 out of 10 times. This is at the end of the evolution. In each generation we ran 200 times, but at the end of the evolution we select the best individual, and then we evaluate it. We check how it succeeded in its task to find weaknesses in the human survivor. And we can see that in most cases, our survivors were very good. There are some cases that they weren't very good. In the paper, we analyzed why is that. I'm not going to go deep into that. But I do want to focus on one thing here, is that our experiment were each time against a single individual and not against multiple individuals. We didn't train against all the individuals together at the same time or something. That's each time, each entire evolutionary experiment, we tried, the purpose was to see if evolution can find the weakness in each of these survivors, but each time it was a different survivor. So this point is important for the next slides. Another interesting thing to see is how the weaknesses that it found. So what you see here, this is Zorg is a competitor from 2012, and the funniest thing in Zorg is that it has an Achilles heel, is that when it starts running, at the very first iteration, it copies something from a specific location at the memory. So the memory is pretty big, and it copies something from this location, and then once it copies it, it's very hard to detect Zorg and to kill it. But our survivors were able to find the exact location in the memory that it writes this data, and pinpoint it and kill this, write to this location at the correct time so that it will catch the Zorg survivor. Another interesting thing is these two survivors, Zeus and Greenies. What you see is that these two survivors, both Greenies and Zeus, write in horizontal lines. So these horizontal lines are Greenies, and here the almost horizontal lines are Zeus. And our survivor realized pretty fast that if it writes vertical lines, it will catch them very fast. So our survivors have no idea. They don't see the code of the evolved survivor doesn't see the code of the enemy, but it did find these problems in their enemies. If you have any questions, you're welcome to stop me. But maybe it's time to say that there's a problem here, because what you see here is that if the survivor is writing in horizontal lines only, then we were able to find it and write in vertical lines. But we realized that, we actually tried it and it didn't work, that if we're trying to evolve survivors against multiple survivors, that each one has different strategy. For example, one survivor is writing on vertical, and one survivor is writing on horizontal. So evolution had very hard time to find a strategy that is able to beat them both at the same time. And so we try to understand why is that. Why can't we win or train an individual that is able to kill two survivors and not only one at a time? And we think that the reason for that is that one survivor equals to one problem to attack, equals to one behavior aspect to consider, vertical line or just vertical lines or just horizontal line and so on. But when you have multiple survivors, you need to write one assembly code, one short assembly code that handles multiple behavioral aspects. And to combine all these behavioral aspects into a single code, single assembly code, it's very hard. And I'm not saying that it's not impossible. In object-oriented, you define, you program different aspects in different methods and different classes. But in short assembly code, it's extremely hard, and we will solve it in assembly. But for now, let's look at a different approach. And this is where I'm moving on to the next paper. So if anyone has any questions about the previous paper on the work on assembly, please, you're welcome. Okay. So the second work tries a different approach. And here we're trying to evolve behavioral programs, not assembly programs. So I will explain what behavioral programs are. And I'll start with the bottom line. We managed to evolve multi-aspect code very easily. And the secret ingredient was the programming language, the behavioral programming. So what is behavioral programming? So some of you saw my previous lecture here in this colloquium. It was about towards better interoperability between software and AI. There's a link here, and also in my homepage if someone wants to watch this video. But in short, what I try to show there, and I will show it just a bit here, is why behavioral programming and AI works very well together. And I will give some demonstrations about it here. So what is behavioral programming? We should start with that. So it's a programming and modeling paradigm that that in general, what we can say about it is that it's instead of writing code, what you do is you take the requirements and you just write them again, the same requirements, but you write them in a specific way. Okay, I will show it in a few slides from here. You write it in a specific way, and then, but each requirement is translated into a single module, single line of code, or several lines of code. And then we have an execution engine that takes all these requirements together and execute them. And this is how we get the behavior. There's no coding here. So here is a graphic illustration of behavioral programming. You can actually, there are languages in behavioral programming that can, where you can actually draw these graphs and run it. But this is just a graphic demonstration. So let's say we have a system with two requirements. The one requirement is that when the system loads, pour 3 amounts of cold water, and another requirement says that when the system loads, you need to pour 3 amounts of hot water. And when you run this program, what you get is these two programs here are two threads, like in Java threads, two behavioral threads that run simultaneously. Each one is trying to proceed in its own speed. And whenever they get to a yellow point, they halt, they stop. And so since currently we just have two threads, each one of them tries to perform cold, and hot, and then we can get, since they are running simultaneously, we get different type of runs every time we run this program. So first time we can get cold, hot, cold, and then we can get hot, cold, and so on. So there are several ways for executing this program. And now this already is different from how we program regularly, right? In Java, for example, if you want to write these two requirements, we need to decide on a specific order. We need to say, okay, this is how it's going to run. It's going to be 3 cold and then 3 hot or something like that. We write a code that is usually deterministic. It's more simple for us to program deterministically. And so in regular languages, we have overspecification in most of the requirements that we translate into code. We usually do overspecification. So this is the first difference between behavioral programming and regular programming. Now, what happens when you have a new requirement? So for example, let's say we have a new requirement that says that you cannot have two operations of the same type one after another. So you can have 2 cold in a row or 2 hot in a row. And then you have a new requirement, you add a new behavioral thread, because we want to have a perfect alignment between the requirements and the code. So we have 3 requirements, we have 3 pieces of code. And this piece here of code, this module, says that we block hot while we're waiting for cold, and then we block cold while we are waiting for hot. And how it is running? So this is the execution engine that you saw before. What it does, it takes all these scenarios. Here we have 3 scenarios. It takes all of these scenarios, and then it asks everyone, whenever all of these scenarios are reaching to the yellow points, it asks them, what do you request? What do you wait for? And what are you blocking? And then it takes all the requests, it filters the blocked events, and then selects one randomly. So here in this example, right? In this example, at the first iteration of the program, we have one thread is here, one thread is here, and one thread is here. This one is requesting cold, this one is requesting hot, and this one is blocking hot and does not request anything. And so the only operation that can happen now is cold, because hot is blocked. And so this bit, cold is selected, and cold is proceeds to the next yellow sync point, and also this behavioral thread proceeds to the next synchronization point here, and this one stays here because it did not happen. And now this one is here, this one is here, and this one is here. Someone is requesting hot, someone is requesting cold, and someone blocks cold, and so only hot can happen, and so on and so on. This repeats until the program ends, and the only option for execution is cold, hot, cold, hot, cold, hot. So this is behavioral programming. It's a very simple paradigm, and it's very powerful. This is just a toy example, of course. And here's another toy example. What you see here are the rules of tic-tac-toe. Some of the rules, not all of them. So, for example, you cannot mark a cell twice. If it was marked using O or X, you cannot mark it again. And so this is what you see here. This is a cell. This is the requirement. This is the implementation of the requirement. So for each cell, this is the context of the requirement. For each cell, we wait for X or O in this cell, and then we block X and O. Okay? And this is the turns requirement. X and O play turns in turns where X starts. So we have wait for X, block O, and then wait for O, block X, and so on. And this is the winning requirement. The first player to get 3 marks in a line is the winner. So here we have detect X weak, and for each line is can be horizontal, vertical, or diagonal. For each line, we wait for 3 X's on this line, and then we block. We say that X win and everything else is blocked, and we also have a method like this for O, and so on and so on. So back to the work on evolving behavioral programs. In this work, what we did is evolving behavioral programs that will perfectly play tic-tac-toe. That was the purpose. And what the user provided was, terminals, so XO, all the possible events in tic-tac-toe, and a ranking function, a fitness function. So I will talk about the fitness function in a minute, but what the user had to provide is aside from the fitness function, is how to evaluate games. So we generate, these are evolved programs, we generate randomly players for tic-tac-toe, and then we need to evaluate these individuals. So we run them like before, we run the game, and we get a trace of the game. We know what he did. It was X 0 0, and then O plays 1 1, and so on. So this is one trace, a second trace, and so on. And we can evaluate these traces. We can see if the individual played correctly or not. And the first question that some of you might want to ask, but afraid to ask, I don't know why, is why not use GitHub Copilot? I mean, it's a simple problem, right? Tic-tac-toe, you can use GitHub. And there are several reasons for that. First, this work was written before the breakthrough of LLMs, so we have this advantage. But there's a better reason for that. LLM needs text. They need description of the desired behavior, requirements, something. Here we only have run traces, right? This is what we have. Or simulator. We have simulator or just run traces, a log of a system. And we want to generate a program that generate these traces or generate good traces. And so LLM is not going to help us here. And another thing to notice here is that it's not a very simple problem, because what we're trying to do here is not to generate code that plays tic-tac-toe. That's very simple thing to do. What we're trying to do is to consider all these different aspects of playing perfectly. There's a strategy for playing a perfect game. And we're trying to generate code that is modular, that you can actually look at it and say, okay, this code is in charge of this requirement, that this code is in charge of that requirement, and so on. So we want to generate modular code, not something that plays tic-tac-toe perfectly, but something that is interpretable and you can understand that, and it's modular, and so on. And that is something that was actually not done before using genetic programming or any other method, as far as I know. And so again, we need to define representation, genetic operators, and fitness function. And again, there's a fitness function. I'm not going to dive deep into this fitness function, but in general, it looks at the trace and says if the trace was good or not good, according to the tic-tac-toe rules. But it still didn't work very well, and we generated to improve it. We needed a way, so the stir space is very huge, and it didn't converge. fast enough, or it even didn't converge in most of the cases. And so to do a better, to do better, we needed to improve the genetic operators. And what we did here is we took a fault diagnosis method. This actually came from a lecture that I heard from Mary Kalech, who is here, I think. I saw him before, and one of the student who worked on this was in his course. So this is how the idea came. And so what we try to do is to detect the malfunctioning nodes, the malfunctioning code that cause problems, and to replace it with a better code, and to detect the good code, and to propagate the good code to the entire population. And this is the idea here. What we did, I'll show it here. So during fitness calculation, we watched the calculation, and we tried to detect if there were good actions and bad actions. If there was a good action, for example, our player was able to block the opponent or to win the game, or if, on the contrary, there were bad behaviors. So we detected these important, significant event occurrences, and we marked in a table, we marked all the places that were involved in this important behaviors, in significant occurrences of good or bad behavior. And so we were able to statistically identify which part of the code was good and which part of the code was bad. And then our crossover and mutation operators were able to utilize this information to choose more likely places to be better. So for example, during crossover, we wanted to propagate the information, the good information. So we gave higher probability for good scores for good individuals or good places in the individuals that were involved in significant good events and so on. And the result was that we created almost perfect players, and the smart operators indeed improved the exploration of the search space. And the evolved players were modular, interpretable, and actually very similar to handwritten players, part of them. So for example, here's a behavioral thread that for each, in the context of CTX1, I will show you in a second what is CTX1. But in the context of CTX1, it waits for X and then blocks, it waits for X on one of the cell, and then blocks O on the second cell. And apparently CTX1 was a list of pairs in lines. So if you recall, before we had the requirement that wait for 3X and then declare that O win, but there are also wait for 2X and block the third X, or wait for 2O and block the third O, and so on. So there's the strategy of blocking the enemy. So this is a bit thread that blocks the enemy. It waits for one and then blocks the other one. So it's interpretable and modular. The code is structured and built out of many bit threads that you can actually interpret them. So that's a great point. They are modular and interpretable, and it can be useful for log mining. For example, if you have system logs, so you can use this method for understanding these system logs, for mining them and generating detecting patterns. And actually, we can also detect anti-patterns. So for example, if the pattern in the system log is that if something doesn't happen, then something else won't happen or stuff like that, it will be very hard to detect such patterns using, I don't know, neural networks, because they are used for detecting patterns, not anti-patterns. But if you want to detect anti-patterns, behavioral programming can be very useful, because you can define what must not happen and not only what must happen. So this is definitely one of the research directions that we want to explore. And it's very effective when you only have simulator or system log and you don't have any text. But what can we do if we actually have requirements or we have text? Can we do something better? And this is where I'm going to the third topic. So if anyone has questions about the second topic, I'll be glad to answer. If not, I'm going to drink some. Okay. So the last part of the lecture is about generating source code from requirements, and I called it from requirements to source code for real. And I know it's not a good title for a paper. It's not really the title of the paper, it's only for this presentation. So the original paper from requirements to source code was published in 2022 before ChatGPT. And the generated code was written in using behavioral programming requirement-driven paradigm, so it seemed like a good name back then. But now what I will show you is how we are actually converting actual requirements in text into BP code, and we do that automatically using Copilot or ChatGPT or LLM in general. One thing to note here is that when we try to define requirements, we specify them in terms of what the system must do, may do, or may not do. This is how we define requirements. But computers have to receive instructions for what to do at any given moment. You cannot tell them what to do, what may happen or may not happen. You just have to tell them all the time what to do. And since we cannot just write programs like that, we need to translate the thinking from inter-object scenarios, how we think about requirements, into objects and the interface of each object. We need to do this translation. This is why we have the design part of programming. It helps us to transform the thinking from inter-object scenarios into intra-object specification. And so let's jump into a demonstration. So okay, so what you see here is it's VS Code. You're all familiar with that. And what I'm going to do, I'm going to write requirements on the left here. And it will generate code here, and then I will copy it. So I already did it for the first requirement. So what I'm going to do is write a system that, a model of an online shopping system called PrestaShop, like Amazon. And I want to test it. I want to check it. I want to write a model of this program. And so the first requirement defines the entities of the system. An address has a street, city, country, and so on. Customer have email, first name, and so on. Admin has email and password. Product has a name, price, and stock. And I want to generate an initial data. And this is the initial data. And this is the code that was generated. So we have the entities and the context population for the first requirement. The second requirement, and I know this is not how you write requirements. I'm going to answer about that after the demonstration. The second requirements specify the context of the requirement. So I do have a requirement. I will show them in a second. Like, for example, for each product and customer, go to the main store page, log in, add some product to the cart, and then log out, or check out, and check that the price is correct, and so on. So there are stories, there are user stories or requirements that describe the behavior that I'm going to talk about. But these requirements, like all requirements, are in a certain context. So, for example, okay, maybe I'll just write down the requirement here. So I'm going to write a requirement which is this one. For each product and customer, go to the main store page, log in, add the product card, checkout, and so on. And this requirement is in the context of product and customer. There are two contexts for this requirement. And so what I'm going to do now, I'm going to start with all the context definitions that I'm going to have in my requirement document. So I extracted from the requirement document all the contexts. And I'm going to add here the implement command. Okay, so I've done the preparations, and now I'm going to start with the actual behavioral requirements. Which, so this is the product, the requirement that I talked about before. What you see here, there's a B thread, a behavioral thread that, let's put an enter here so you'll be able to see it. So in the context of product and customer, for each product and customer, we only have one product and one customer. So there's only one combination for this. For each product and customer, go to main login store page, login event, request to go to the main page, then request to login, then request to add product to cart, request to checkout, and request to verify that the cart price is correct. And this is, as you can see, it's very aligned to what you see on the left, to the requirement itself. And if I run this, so as I said, behavioral programming is it has semantics, right? You can actually run this. And what I did now, I explored the entire state space of this program. And you can see that this program has only one story. So there's only one way to look at this, to run this program. Okay, so I'm going to add another requirement. Given a product and an admin, go to admin page, fill in the login details, and change the product stock to 0. Okay, so here's another story. And again, I'm going to run this and generate the graph. And what you see here is it's a much larger graph, right? And it combines all the possible combination of this behavioral thread and this behavioral thread. So there are 5 events here and 3 events here. And so we have all these combinations. At the first event, we either go to the main store page event, or we either go to we either call the go to admin page event. And so these are the 2 options, and then we have other options and so on. So this is the interleaving of the 2 behavioral threads. And we can go on and on. We can also say what must not happen. I can say the admin changed the product stock to, okay, maybe I just write the requirement first. So I can say that an out-of-stock product cannot be added to cart. I want to block these events from happening. You see, I'm using the block idiom. I don't want it to happen. And it's not going to work. There's a mistake here. What's going to happen now is that it will look exactly the same. The graph didn't change. And the reason for that is that the LLM didn't recognize that that if I change the product stock to 0, I need to actually change the state of the system to the state of the product to be 0. So I'm going to tell it explicitly. So it's not perfect yet, of course. think it will be okay now. Okay, so it changed the graph, and now the graph is a bit smaller. It changed. I don't know if it's not necessarily smaller, but it changed. And some of the stories that were possible before, now they are not possible because you cannot change the product to 0 and then add the product to the cart. So this is the demonstration. Any questions so far?
Just one path remain?
No. There are still many paths,
Ah,
but less paths than before.
okay.
At least this is what should be. I'm not sure that it's exactly what happened. Maybe there's another mistake here. It's not perfect yet, of course. One of the things to notice here is the ability to translate requirements directly into the code. And you can see it's not like, okay, I'm going to, for example, when you use Copilot for, I don't know, writing Java code, you still need to do the design phase. You cannot give it requirements of the entire system and then tell it, okay, just program the system. If it's a very small system, maybe, but very fast, it will not succeed. You need to, Copilot is very good if you give it a class, a definition of a class, a definition of a method, and then it will be able to generate it very good, but not requirements. And the reason for that is that the difference between the inter-object specification and the intra-object specification. But here, when you translate requirements into behavioral programming, you don't have this phase of changing of design. You just translate them as is. So this is the first thing to notice here. And the second thing to notice here is that you have kind of a verification validation step here. So you write a few requirements and you translate them into code, and you can immediately run this command and see how it is translated into graph. You can see how the requirements interact. And if there are problems in the requirements, you detect it very early. And you can actually also generate code from that and implement the system this way. But even if you just want it for requirements engineering, this is a very powerful tool.
So can I ask a question here?
Yeah.
In the case when there is no item on stock, and you didn't explicitly say, tell the customer there's no item on stock, it's going to be delayed or something. So is it able to identify some kind of an exception saying that your order cannot be completed, so you need to add another step in the program which says, tell the user the message that you're not going to get it because it's not on stock, or something along those lines. You should be able to do that.
So there are two solutions for that, two answers for that. So first, if you see here, I said that given a, where is it? An out-of-stock product cannot be added to cart. This behavioral thread is in the context of product out of stock. Mm-hmm. So the moment you try to do something with a product, the moment you try to add a product to a product that is out of stock, it will block it. But you can add a requirement that says if a product is out of stock, or maybe for each out of stock product, I don't know, suggest the user to buy another one. Okay, for example, I think this is what you asked, right?
Yeah.
So I can write this requirement. I'm going to remove these two queries because it already defined them. So for every out of stock product, this if is actually, oh yeah. So that's nice. So it takes it actually works, I think. It takes all the in stock products, and then if it's bigger than one, it suggests it requests a different product.
Okay.
And then this behavioral thread will interleave with the entire system. So whenever you have a path that one of the products is becoming zero, the stock is a zero, then this option will suddenly appear. So you will have in different spots of the graph, you will have new subtrees.
Achia, we have 5 minutes to the top of the hour. I
So-
don't know if
Yeah, so basically I finished.
maybe some questions and answers.
Yeah, that's
Yeah.
that's a good point.
I have a question about the behavior programming, but which is maybe did you think about trying to embed the histories into text, like creating a fake quote unquote document by because the histories if you treat each event in the game history as like an embedding, and you put them together, and so you can do word to vec on top of that. You can try to embed it into text. And
So I'm not sure on which work you are talking about. The BP code evolution or the BP code LLM?
the behavior, you said that with the behavior programming work, you asked why LLM was not used. Jokingly, you said it's because it was done before, but then you said probably you cannot. And I wonder if it can be done by like tweaking the representation of the histories into text that represents the history order.
So I actually have
I wonder if you consider that.
So yeah, actually we have a work that is doing something like that. It's approaching in a BERT-like. So it looks at the behavioral program as a sentence and then uses BERT to hide some parts of the program and then tries to.
That's exactly
we have
what I had
something
in
like
mind.
that.
Yeah.
We have a work on that. Yeah.
Okay. Are there additional questions to Achia?
So I had another question. If you write the requirements in the way you're writing, can you produce the output code in any other languages like Java or Python or whatever? So it can actually integrate with the real systems?
So behavioral programming integrates with other systems, and the way it does it using listeners and actuators. So we have a company that is based on behavioral programming called Provengo, which is a testing company. And what we do there is we generate the test models using the way you saw just now. And then we connect it using Selenium and Appium and so on. So actuators that actually do things on websites or mobile applications and so on. So we can actually connect real systems to these models, executable models. But we are not translating it into a program. The idea is that it's an executable program. You can basically generate the graph and then select one of the paths, and this is a program. But we don't want to do that because we want to be able to do all the possible things, all the possible paths.
And also, I assume you can create test cases, right? What is the set of test cases which would make sure the program satisfies the requirements you gave?
Right. So I talked about it a bit in my previous lecture, and yes, this is of course part of what we do in the company. Yeah, we take this graph of the all possible paths in the program, of the program, or of how users interact with the program, and then we take all these huge graph and then we use some techniques to create test cases that test suites that cover the behavior effectively.
Thanks.
One more question.
I think it's time to wrap up. Yeah, very interesting. We
Thank
did
you.
attract many, and I think there would be follow-ups following this lecture. So thanks a lot, and we have the
Thank you.
recording. We put it on the website once it's ready. So thank you everyone for attending, and meet you soon, in another month from now.
Thank you.
Thank you.
Thank
Bye-bye.
you.